Hi everyone, in this series we are going to revise complex numbers. Specifically, in this part we are going to review the different forms for representation of complex numbers like the rectangular form, polar form, and graphical form. In the next part of the series we are going to revise the arithmetic operation, addition, subtraction, multiplication, and division, and solve a couple of examples. So let's get started. So the main motivation behind defining the complex number is that we had to do solution for some complex equation that required having the square root of a negative numbers. Unfortunately, the set of real numbers doesn't have support for the square root of the negative numbers. So we introduce the imaginary numbers to be able to solve such equations by providing a solution to square root of a negative number. So our way to define those imaginary numbers is that we introduce the imaginary unit j. You may have seen this unit before in your math class as an I, where I or j by definition is the square root of -1. In electric engineering, we prefer to use the symbol J to denote an imaginary number because we already have I reserved for the current. So now a complex number will be a number that has both real and complex part. So the general form for a complex number would be A plus JB. So now you can see that we have the imaginary unit J. So we call this number here the real part of our complex number, and B as the imaginary part of the complex number. So far so good. So now let's talk about different representations of the complex number. So what we have seen right now, a complex number is represented as A plus JB. This is what we know as the rectangular form. So let's tab on this form one more time and introduce two other forms like the polar form and the exponential form. So the standard version of the complex number is composed of a real part and then the imaginary part. So if I have a number z as a complex number, it would be written as a real part x plus the imaginary part y. This representation can be plotted into the complex plane, which is similar to the real number x, but here, since we have two pieces of information, a real part and an imaginary part, the complex plane is a 2D part, where on the horizontal axis we have the real part, on the vertical axis we have the imaginary part. So if I have a number z equal to x plus jy, so we have x units on the real part, and then we have y points or y units on the imaginary part. So this would be the location of that complex number in the complex space. Now looking at this point, I can define a vector starting from origin to this point, which is a complex point. So any complex number is a point in the complex space. I can define a vector extending from the origin to ZZ. We can use this vector as another representation to represent that complex number, where we consider the length of the vector as the magnitude of this number and the angle of this vector as the phase of that number. And this is formally known as the polar form. So in the polar form, the complex number is written in terms of a magnitude and an angle. Specifically, it would be written like that, where r is the magnitude of that complex number, or the magnitude of the vector connecting the origin to the location of this complex number in the complex space, and phi is the angle of that vector. So now, if I have this number z equal to x plus jy, how to get the magnitude and phase? So if you look at the graphical representation, so we have x units on the x-axis, which is the real x, and we have y units on the vertical axis, which is the imaginary axis. This makes a right triangle and we would like to get this length here, r. Using the geometry, we can see that r is equal to square root of x squared plus y squared. So basically, the magnitude of the complex number is the square root of the real part square plus the imaginary part square. So how about the angle? We can use this angle using the trigonometry. So this angle phi is equal to tan inverse. We have the opposite side, which is y, over the adjacent, which is x. So the angle is phi, which can be computed using tan inverse of the imaginary part over the real part. So this is what we have: magnitude square root of real part and imaginary part square, and the angle would be the inverse tangent of the imaginary part divided over the real part. Okay. And once you have the magnitude and phase, your complex number in the polar format can be written using this form. Okay. Now can we reverse it back? Assume that if I know r and I know phi, can I get the real part and the imaginary part? The answer is also yes. This is the right triangle, and you can use rules of projection. So x would be the projection of this vector over this side. So x would be r, and then we have an angle phi cosine phi. And y would be the projection of the same vector onto that vertical axis. So y would equal to r sine phi. Okay, so yep, we can go back and forth between the two representations. X is r cosine phi and y is r sine phi, where x is the real part and y here is the imaginary part. So once you have x and y, you can write down your number into the rectangular format as z equal to x plus jy, which is equivalent to r cosine phi plus j r sine phi. Okay. Now, inspired by that representation, the polar representation, we can introduce another equivalent form, which is the exponential form. So this number here represented in the polar format, an equivalent exponential format using a complex exponential would be r e j phi. So here I have a complex exponential with a magnitude r, same as the magnitude, and the complex exponent is the angle of my complex number. So this number here, 3 angle 30, this is a complex number whose magnitude 3 with a phase of 30 degrees. The equivalent representation and the exponential form is 3 ej30. Okay, and this exponential form is naturally fit to our analysis because if you recall, this exponential form using Euler formula, a complex exponential actually corresponds to a complex sinusoid, and this is known as the Euler's identity. So ej phi is equal to cosine phi plus j sine phi. Now I have a number z in the exponential form rej phi. If we apply Euler identity here, replace the ej phi using the complex sinusoid, so we have cosine phi plus j sine phi. Distribute the multiplication of r. We have these two parts. If you recall from 2 slides ago, this is how we converted the polar form to the rectangular form. So this is the real part x, and this is the imaginary part y. So yep, it is equivalent representation. It gives me the same relationship between polar and rectangular. So Euler formula or the exponential representation is also a valid representation for the complex number. So let's wrap up with an example. So if I have a complex point here, z, this is a complex number. So you can see that it has 3 units on the real axis, has 4 units on the y-axis. So the rectangular form for this number is 3 plus j4. Okay, we can get the magnitude and phase. So the magnitude r would equal to square root of 3 square plus 4 square. This gives you square root of 25, which is equal to 5. So, and the angle phi is equal to tan inverse of the imaginary part over the real part, and this gives us 53.1 degrees. So this is the rectangular form, and then using the magnitude and phase, we can represent the number into the polar format. It would be 5 of an angle 53.1, and also in the exponential format, it would be 5 ej the angle, which is 53. So any number can be equivalently represented in one of the three forms. As we're gonna see in the next video, one form might be easier for addition, while the other would be easier to do the multiplication. However, all three forms are equivalent representation of the same complex number. So in conclusion, in this video, we quickly overviewed the need to introduce the imaginary numbers, and the imaginary unit is J. We use it in electrical engineering. We also talked about the real part and the imaginary part of a complex number, and reviewed different representation in the rectangular form, the polar form, and the exponential form. And we used graphical representation to map between the polar and the rectangular form, and we also used Euler identity to prove that the exponential form is equivalent representation to our complex number. Thank you so much for listening.